For decades, one category of software bugs has cost the industry trillions of dollars, and that's memory bugs. Whether it's a null pointer exception in Java or a use after free bug in C or C++, these issues have caused crashes, security vulnerabilities, and countless hours of debugging. So in this video, let's do something fun. We're going to design a programming language from scratch. But our programming language is going to be special because it will have a memory model that eliminates memory bugs altogether. So let's dive right in. By the way, there are only 24 hours left to register for the Rust Live Accelerator June cohort. So click the link below if you're interested in direct mentorship from Let's Get Rusty. Now back to the video. To build a language that eliminates memory bugs, we first have to answer 3 fundamental questions about memory. First, when the program is running, who allocates and deallocates memory? Second, how do you share memory among different parts of a program? And third, how do you prevent invalid memory altogether? These are the 3 fundamental questions we have to answer about memory management when designing a language. If we're able to answer all 3 questions well, we should be able to design a language that gets rid of memory bugs altogether. Let's take them one at a time. Problem 1. Who allocates and deallocates memory? The first obvious option is to make the programmer do it by hand. That's what C does. Programmers have to manually call malloc and free to allocate and release memory. If you forget to free memory, you'll end up with a memory leak. If you free the same data twice, or free the data too early, the program can crash, or even worse, become a security hole. The second option. Instead of making the developer allocate and free memory by hand, we hand that job to another program. The second program runs alongside yours and cleans up memory for you in the background, using something like a mark and sweep algorithm. This approach is called garbage collection, and languages like Java, Python, and Go all use garbage collection. But garbage collection brings its own problem: performance. The collector pauses your program to clean up memory. These pauses hurt performance, and you don't get to control when they happen. Is there a third option, one that combines the safety of garbage collection with the performance of manual memory management? Let's engineer the third option together. Remember that we like the safety of garbage collection. We just don't like the performance compromise. So instead of cleaning up memory at runtime, why don't we move the memory management to compile time instead? We can add a step to the compiler itself, a step that enforces proper memory management. More specifically, the compiler will enforce that every value has exactly one owner, and that owner is responsible for cleaning up the value's memory when it is no longer needed. For example, the vector 123 is owned by the data variable, and when the data variable goes out of scope, the compiler automatically inserts the call that frees that memory. No background process, no manual free. The work happens at compile time, without runtime performance drag. And since the compiler rule is all about maintaining clear ownership of a value, why don't we call it the ownership rule? With this ownership rule, when you hand the data to someone else, the ownership of the data moves to the new variable. So there's always exactly one owner responsible for freeing the memory. Great, so that's how we handle who allocates and deallocates memory, all while maintaining peak performance. But what about problem 2? The problem of sharing memory among different parts of the program. Remember our ownership rule from problem 1? The ownership rule is strict. Only one part of the program owns a piece of data at one time. This restriction could become an issue for us because real programs often need many different parts to use the same data at once. So that's the problem we need to solve. How do we share memory safely? Because if multiple parts of the program share the same data, and one of them modifies it or frees it, every other part could be left looking at invalid memory. Here's a clever solution. Instead of completely handing ownership of the data from one part of the program to another, we can allow other parts of the program to temporarily borrow the data while the original owner keeps ownership. Borrowing gives you permission to reference the data without taking ownership of it. You can use the data, but you're not responsible for cleaning it up because it still belongs to the original owner. In this language we're designing, we'll use the ampersand symbol to represent a borrowed reader to the data, and a mutable ampersand to represent a borrowed writer to the data. As we can see from both the code and the visuals here, the A and B variables borrow the same data, but neither one can modify it. Because they're only reading, it's perfectly safe for both readers to exist at the same time. But if we also allowed a writer to the same data, it could modify the data while others are reading it, leading to inconsistent results. To prevent that, we will add a step to the compiler which enforces a simple rule. You can either have many readers or one writer, but never both at the same time. While we're here, let's update our compiler to enforce one more borrowing rule. A borrow can never outlive the data it points to. If the original data is freed while a borrow still exists, the compiler rejects the code. That means borrowed references can never point to freed memory. In other words, dangling references become impossible. Okay, this idea of borrowing data seems pretty useful. So why don't we formalize it and name it something like the borrowing rule? And best of all, there's still zero cost for runtime performance, because every one of these rule checks happens at compile time. Fantastic, problem 2 is now solved. We know how to share memory while still maintaining clear ownership, thanks to our new many readers, one writer borrowing rule. But we still have one final problem to solve. How do we prevent invalid memory altogether? At first glance, that might sound like a strange question. Haven't we already done that? Well, almost. The ownership rule we introduced in problem 1 guarantees memory is freed exactly once. The borrowing rule we introduced in problem 2 guarantees references can never outlive the data they point to. That means use after free bugs, double frees, and dangling references are already gone. But there are still two important sources of invalid memory left: the infamous null pointers and sneaky data races. The first is null, which is a reference that points to nothing. In our example, if we try to get the value at index 9 in the data, it results in a null pointer exception in languages like Java because that index doesn't exist in the data. This is an extremely common and annoying source of bugs in production. It's so problematic that even its inventor, the person who invented the concept of null, Tony Hoare, famously called null his billion-dollar mistake. So what can we do? Is there any way we can prevent null pointers? Well, here's a crazy idea. What if we just don't allow nulls in the first place? Instead, when a value might be missing, we make that possibility its own type, a type that the compiler can check at compile time. This forces us to handle the case where the value is missing before the program even runs, without adding any runtime performance costs. And in the case of the language we've been designing throughout this video, let's make that compile time check type either some value or none. This way, the compiler forces us to handle the none case before we ever get to the value itself. We cannot accidentally treat a missing value as a real one, because the compiler will not let us ignore that possibility. We've added a tad bit more code, but now nulls are impossible, and that's a trade for memory safety we would make every time. Okay, the first half of problem 3 is now solved. Nulls are handled. Now, let's address the second half of problem 3, data races. Data races happen when two or more threads try to access the same memory at the same time, and at least one of the threads is trying to perform a write to the same memory. Data race bugs can be notoriously difficult to even reproduce, let alone solve, because they often depend on timing and the program's execution. Fortunately, for the language we're designing here, we don't actually have to do anything extra to prevent data races. The borrowing rule we introduced in problem 2 already forbids that pattern. The rule enforces many readers or one writer, never both. So if we extend that rule across threads, data races become impossible. And that makes concurrency in our language safe. In fact, we can even call it fearless concurrency. The final problem, problem 3, is now solved. Let's take a step back. We set out to design a language where memory bugs cannot happen. 3 problems, 3 answers. And together, these 3 answers are the entire rule set our compiler enforces. One owner per value freed automatically, which prevents double frees and use after free errors. Borrowing with one single rule, which prevents dangling references and also makes data races impossible. And not introducing null at all, and instead representing a value that may or may not exist with its own dedicated type. We've now designed a language where these trillion-dollar memory bugs cannot happen. And at this point, you probably already caught on. This language is not something we just invented in this video. It's Rust. Every single decision we just made, one owner, borrowing data, no null, all while keeping fearless concurrency, is already built into Rust. But we didn't just study Rust rules and memorize them for the sake of it. We re-derived them from scratch, following logical principles. And that is the genius of the Rust memory model. It isn't any one feature. It's that 3 different problems turned out to share one coherent set of answers. Now, understanding these ideas is one thing. Applying them to real-world production Rust systems is another. So if you want to master Rust to the point where you can get paid to write Rust professionally, I want to invite you to join our Rust Live Accelerator mentorship program. After you join, you'll be mentored by professional Rust experts who will give you code reviews, help you with architecture, and get you to the point where you can build sophisticated, production-grade Rust software with confidence. On top of that, we have a team of recruiters and career coaches who will help you turn those skills into high-paying Rust roles. We've helped hundreds of developers, and we want to do the same for you. The application period for the June cohort is closing in only 24 hours. So click the link below to reserve your spot. And you'll also get our 3-step Rust developer roadmap as a small gift. So tap the link, apply to see if you're qualified, and I'll see you inside.